expectation values, which is something we started on Wednesday. And so we'll start with just reminding everybody of a couple of obvious things. So before we jump into the quantum world, let's just remember what would happen in our everyday world when we had some kind of game of chance. And so let's just imagine that we placed our playing cards down on a table, and they were randomly sorted, and the person picking up the cards had no idea how they were sorted. So a couple of things that you could know about this experiment is, number one, if you flip up one of the cards, when you actually reveal what's in the card, it's going to be an actual card, right? You're going to get a 1, a 2, a 3, a 4, etc., a jack, queen, king, ace. You're not going to get some sort of hybrid between different cards, right? You're always going to observe an actual card. Okay, that's obvious. And then the other thing that you can say is that if you do this experiment multiple times, so you flip up card number 1, flip up card number 2, and so on, and you take the average of the results, if they're all numbered cards, you can just take a numeric average. That would be pretty easy. The average is not required to be one of the actual values of the card. So we all know that, and that actually has a lot in common with the types of experiments that we talk about when we talk about expectation values. So let me just remind you of the type of experiment that an expectation value relates to. And so if you look up if you just imagine some system, and here what I'm actually referring back to our harmonic oscillator system. So you can imagine that the system that we have is actually going to be a diatomic molecule, because that was a system which was very readily modeled by the harmonic oscillator. So we can just say that this is something like hydrogen chloride or carbon monoxide, if you like that better. And so anyway, this is a statement that our system, our molecule, or diatomic molecule, is described by this particular wave function, which is denoted big psi 1 is equal to some amplitude times little psi 1, which is the first excited state of the harmonic oscillator, plus another amplitude times psi 2, plus another amplitude times psi 3. And so the couple of things that we know about these little psi's, these are the energy eigenfunctions. So they have well-defined energy values individually. So in particular, psi 1 has energy E1, where we just replace this number n with the number 1, add it to 1/2, multiplied by h bar times square root of k over mu. Okay, and we're going to work in our favorite unit system, where h bar times square root of k over mu for our molecule is equal to 1. So energy associated with energy eigenfunction 1 is literally the number 3/2 unit of energy, and energy E2 is 5/2 unit of energy, E3 is 7/2 unit of energy. Okay, so that's all well and good. So individually, the energy eigenfunctions have well-defined energy, but the state of our diatomic molecule is not a pure energy eigenfunction, it's actually a superposition. So our diatomic molecule described by big psi 1 does not have a well-defined energy. So we can't really speak about it having energy E1 or E2 or E3, but what we can talk about is its expectation value. And so we'll calculate the expectation value in a second, but let's just remind ourselves of what the expectation value tells us. So number one, it tells us about the average outcome of experimental measurement of the energy, but it's a very particular type of experiment that you do. So you have to imagine that you have a device capable of measuring the energy, which I'm denoting by this blue box with a white E on it. So that's my Stern-Gerlach box that can measure the energy. And I have many copies of my diatomic molecule, all of them prepared in the same state psi 1. And I'm going to send those molecules one by one into my Stern-Gerlach box. And then when I do that, I'm going to measure an energy. That's going to be the purpose of the Stern-Gerlach box. It's actually going to report to me an energy value. And then the result of the measurement will be to collapse my wave function into a state of well-defined energy. So this box right here, this represents one possible outcome of such a measurement. Diatomic molecule described by big psi 1 goes into the box. I measure energy E2, and then I collapse into state psi 2, little psi 2. The energy, the third energy eigenfunction, aka the second energy eigenstate. Just a quick reminder that the harmonic oscillator starts with n equals 0. So the ground state is psi 0, first excited state is psi 1, second excited state is psi 2. So how likely is that outcome, by the way? So if I look at my amplitudes, that actually tells me about the likelihood. The amplitude squared in this case, which is going to be 6 over 10, relates to the probability that I'm going to collapse to state psi 2 and measure energy E2. So this is one possible outcome. Another possible outcome is that I send my diatomic molecule through the box. I measure the energy E1, and I collapse to state psi 1. And the probability of that happening is 20%, given that my coefficient behind psi 1 is square root of 2 over 10. So the coefficient squared is 2 over 10, or 20%. Okay, finally, third possible outcome, I send my diatomic described by big psi 1 through the Stern-Gerlach box. I measure energy value E3, and I collapse to state psi 3. And the probability of that happening is 20%. Again, because the amplitude is square root of 2 over 10 behind psi 3. Okay, so we've seen that a few times, and hopefully this is becoming more familiar to you. But let me point out one other very important fact, which is that if I just consider this first outcome, psi 1, big psi 1 goes into the box, I measure E2, which means I've collapsed to little psi 2, the second excited state of the harmonic oscillator. Okay, so now my wave function for my diatomic molecule is exactly an energy eigenstate. That's what this outcome is supposed to tell me. And so now I can actually say that my state has energy E2. It is in a state of well-defined energy. So subsequent measurements of the energy, for example, sending it through this Stern-Gerlach box at the bottom, is going to always return E2. The probability of that outcome is 100%, because what I've done is I've already collapsed from the first measurement into an eigenstate of energy, and so any subsequent measures of the energy is going to return the same value of the energy. So it's very important that you realize that the expectation value is going to measure the average outcome of the energy when you make many independent measurements, meaning you send one particle through a box, you send another particle through a box prepared in exactly the same way, and so on. You can't just repeatedly measure the same particle. That will not give you the same outcome. Okay, so here's our definition of the expectation value. So the idea is that if we know the wave function, we can actually predict the outcome of that experiment. We can predict the average energy measured in the experiment described before, where we make many independent measurements of the energy on systems all identically described by psi 1. So mathematically, here is the expression for the expectation value. And so what you should try to do now is imagine for yourself how you're going to approach taking this integral, right? I need to act on the wave function psi 1 with the Hamiltonian operator, and then multiply the result by psi 1 star and integrate over all space. So take a minute to think about how you're going to do that. You can press pause while you work through your notes, and in just a minute I'll show you the steps. Okay, now that you've had a chance to work on that, let's take the next step. So if you happen to know that what your wave function is in terms of the energy eigenfunctions, then the natural thing to do is to actually expand your wave function in terms of those energy eigenfunctions. And the reason why you want to do that is because this Hamiltonian operator can hit individually every one of these terms in the expansion, like so. So the next line down, we've just moved our Hamiltonian operator so that it's hitting each of the energy eigenfunctions in the expansion, and by the virtue of these things being the energy eigenfunctions, right, they satisfy h psi equals e psi. So we can actually get rid of the operator in the next line and just replace it with its corresponding energy eigenvalue, right? So h hat acting upon psi 1 is equivalent to the energy value E1 times psi 1, and so on. Okay, now we worked through this on the board on Wednesday, so I'm not going to show you the steps again, but if you're unfamiliar with, or if you're uncomfortable with the steps, I encourage you to FOIL out this, this integrand and convince yourself through the use of this identity, which is basically a statement that the energy eigenfunctions are orthonormal, right? They integrate with themselves to the value 1. They integrate with all of their partners with different indices to the value 0. So what you can basically do is cause, there's going to be many terms, right? Actually, 9 different terms in this expansion, but only 3 of them are going to survive. Basically, psi 1 star psi 1, psi 2 star psi 2, and psi 3 star psi 3 are going to survive, and those are each going to individually integrate to 1. And the result will be this weighted sum of the energy eigenvalues that you see here. And so the weighted sum of these energy eigenvalues turns out to be 5/2. And 5/2 also actually just turns out to be the actual E2 energy eigenvalue. So that's not to say that this is a generic result, right? This is kind of an interesting feature of the particular superposition we have, and also an interesting feature of the progression of energy eigenvalues in the harmonic oscillator. They have linear spacing. So this wouldn't necessarily happen. Just be cautious of that. Okay. And so just a reminder then what all this thing means is that if we went through that experiment we described with the multiple independent measurements, took the average of our energy outcomes, right, then the expected average is going to be the number E2 or 5/2. And that's exactly what we calculate with our expectation value. Okay, fantastic. So let's look at our other system that we wrote down on Wednesday, which is this another diatomic molecule described by the wave function big psi 2, which now is a superposition of not 3 energy eigenfunctions, but 5 energy eigenfunctions. So it's got the ground state in it, psi 0. It's got the first excited state, psi 1, second excited state, psi 2, and so on. Okay. It's got exactly the same energy eigenvalues as before. It's the same system, just a diatomic molecule modeled as a harmonic oscillator, just different wave function. Okay. And so, again, I can think about sending my diatomic molecule through my Stern-Gerlach devices to measure the energy. And again, I've listed some possible outcomes, or actually the only possible outcomes, given the form of the superposition and the probabilities of those outcomes. So again, the most likely outcome is I send my diatomic into the Stern-Gerlach box. It reports the energy value E2, meaning that after the measurement, I've collapsed to energy eigenfunction psi 2. And the probability of that happening is still 60%. And then the other possible outcomes are to measure the ground state energy with probability 10%, measure the first excited state energy with probability 10%, measure the third excited state energy with probability 10%, or to measure the fourth excited state energy with probability 10%. And if I make many independent measurements on many identical systems described by psi 2, and I average the outcomes of these energy measurements, then again what I'll get is, well, it'll be described by this weighted average here, which again turns out to be 5/2, which is the same thing as energy eigenvalue E2. So we have two systems. They have identical expectation values. but they do actually have different distributions in terms of the frequency of outcomes of energy measurements. And so that's illustrated here. So on the left-hand side, we have our diatomic molecule described by big psi 2. So this is the distribution that we just came up with in the previous slide. And then on the right-hand side, here's the diatomic molecule described by big psi 1. Here's the energy distribution we came up with a couple of slides ago. Both of them have the same expectation value. It happens to be energy E2. Okay, so how are these things different? Well, one way that they're different is that the average deviation, meaning the average amount by which a particular outcome deviates from the average outcome or the expectation value, is different for these two. And so how do we describe that? Well, we can talk about the square deviation of a particular outcome. So I'm going to write a particular outcome of an energy measurement, E sub I, and the deviation, the square deviation of that outcome from the average is just E sub I minus expectation value of E, that whole quantity squared. And so you might remember that it's very common to take the square of these deviations in statistics because, well, we can have deviations that are positive and deviations that are negative, and in fact, both of these distributions, if you have good statistical intuition, you might realize that the deviations, if unsquared, will exactly cancel each other out. And so there is, of course, a real standard deviation to these distributions, and so we'd want to account for that. So anyway, we're going to square the difference between individual outcomes and the average. And we're going to average over all of those possible values. And so how actually do we do that? So here's basically the expression for the uncertainty in energy. And basically what it is it is the standard deviation of the energy measured in the same way we talked about the expectation value. So making many independent measurements on identically prepared systems. And so how do we actually calculate that thing? And so first, actually, before I show you how to calculate it, what I want you to think about for just a minute is which one of these systems do you think actually has the largest uncertainty in energy, which has the largest standard deviation? So we'll see how to do that. So basically, you can kind of guess maybe from this expression that the way that we're going to calculate the uncertainty is to basically take two different expectation values, right? We actually already know this term right here. This is the energy expectation value that we already calculated squared. So we get an expectation value of energy and we just square that number. And so we'll deal with how to calculate this term right here, this expectation value of E squared. So just like the expectation value of E involves wave function, complex conjugate, times the energy operator acting on the wave function, the expectation value of E squared is wave function, complex conjugate, energy operator squared, acting upon the wave function integrated over all space. Okay, so let's look at how to do that. I put this up, by the way, just as a reminder. We already calculated. Expectation value of energy. It was 5/2. If we take that number and square it, we're going to get. We should end up getting the number 5. At least I hope that's the case. Alrighty. So what do we do to actually calculate this expectation value? So we're going to set up our expectation value expression the same way as before. We're going to expand psi star on the left-hand side and expand psi on the right-hand side. And again, our energy operators are just going to distribute to psi on the right-hand side. And so what happens when you hit psi1 with two energy operators? Well, energy operator on psi1 gives you E1 psi1, and then take energy operator acting on E1 psi1. It does nothing to E1, but when it hits psi1, it gives you another factor of E1. So the result of H hat on psi1 is going to be E1 squared psi1. Similarly for psi2 and psi3. So what you end up getting down here is E1 squared psi1 multiplied by its coefficient plus E2 squared psi2 multiplied by its coefficient plus E3 squared psi3 multiplied by its coefficient. And then you'll integrate over the entire product of this expansion. Again, it's the situation where you're going to end up with only three like terms that don't disappear in the integral, right? Basically 2 over 10 times E1 squared times the integral psi1 star psi1 plus 6 over 10 E2 squared times the integral psi2 star psi2 plus 2 over 10 E3 squared times the integral psi3 star psi3. And that's just going to give you this right here, which can be expanded using the numbers for E1, E2, and E3 as follows. And so the result of this thing actually ends up being just the number 6.65. Okay, and from before we had E2 squared is 5. So that means that our delta E, which is expectation value of E squared minus the square of the expectation value of E, gives us, and the whole thing square root gives us the number 1.28 with a bunch of decimals behind it. Okay. So I definitely encourage you to work through that example in its gory detail so that you are confident you understand it. But let's, you can pause the slides, of course, but I'm going to go ahead and keep talking just to conclude this little exercise and figure out what the uncertainty for the system described by psi2 is. So again, okay, we want to get, first thing to do is we already know the square of the expectation value of E for the system described by psi2. We calculated that several slides ago. So we just need to get the expectation value of E squared for the system described by psi2. So again, it's this integral of psi2 star H hat squared acting upon psi2. And this is going to work out exactly the same way, where we end up with our amplitudes squared for each term in our superposition. So 1/10 times energy, the ground state energy, E naught squared, plus 1/10 E1 squared, plus 6/10 E2 squared, and so on. So you can expand, of course, all of those terms in terms of the actual numbers that the energies are equal to, and then that gives you the number 7.25. So the expectation value of E squared is 7.25, and the square of the expectation value of the energy is, again, 5. So if we take delta E as expectation value of E squared minus the square of the expectation value, then we're going to get the number 1.5. Okay. So, oh, and here's a typo. This is supposed to be 1.28. Sorry about that, guys. Okay, so so here's the conclusion, right? Which one of these has the largest uncertainty? Well, we figured out that this system here had uncertainty 1.5, and this system had uncertainty 1.28, despite the typo here. So, so of course, this looks to be the broader distribution, so it's no surprise that this is the distribution with greater uncertainty. Okay. And one other thing is, you should think for just a minute what you actually think the dimensions of the uncertainty and the energy are. Are they dimensions of energy, or are they some other dimensions? So think about that a little bit. Remember, the expectation value of energy we determined already had dimensions of energy. We briefly discussed that last Wednesday. So go ahead and think through if you think the delta E also has dimensions of energy. Okay. So that concludes the introduction to uncertainty and our brief review of expectation values. You're going to be stay tuned for a little bit more on some of these unusual, not too unusual, but some of these slightly more complicated questions, some of which we'll discuss in class and some of which I'll discuss in a subsequent video. So here's some other questions just to start thinking about, and I want you to actually just try to imagine if these situations and see if you can arrive at some kind of hypothesis for the answer. So, so first question is, can there be expectation values besides the energy? If so, how do you calculate them? So think about the other kinds of experiments that you can do and ask yourself if it makes sense to do same kind of experiments where you measure an outcome and average over the outcome. Okay, here's another question. Can the expectation values change with time? Meaning, if I have my diatomic molecule and it's 3 o'clock on a Friday, and I perform the experiment I just described, so I have to have a lot of them. So I have a lot of diatomic molecules at 3 o'clock on a Friday. And then, 2 weeks later, I've got the same diatomic molecules, plural, many of them, and I do the same experiments. Will I get a different expectation value? Does it depend on what the expectation value is for? So it kind of spoiled the answer to the previous question. Let's say I'm talking about a different quantity, not the energy, but maybe the momentum or the position or the angular momentum. Can those quantities change in time? Can the uncertainty in those quantities change in time? So can something happen to the distribution? And finally, this is more of a practical question, but our life was made easy by the fact that we could expand our wave function in terms of the energy eigenfunctions with known amplitudes, and then it became particularly simple to calculate the energy expectation value. So let's say either we don't know the wave function in terms of the energy eigenfunctions, or we don't know the energy eigenfunctions, or we're interested in a different expectation value where the energy operator is not the appropriate operator. So what would be the strategy for calculating the expectation value in those cases? So think about those questions. And I hope this was a helpful experience watching these slides. And I'm looking forward to seeing everybody on Wednesday.